All right. Good morning. My name is Brian Harmer. I'm working on my master's in electrical engineering with Dr. Watt, specifically in fiber optics. I don't have my thesis topic set in stone as of yet, so I thought I'd just give you a brief overview of how light propagates through fiber optics and some advantages that fiber optics have over copper wire. So as many of you know, light travels at different speeds through different mediums. So if you give light in the speed of vacuum as variable c, and you give the velocity of the light through a different medium as v, that ratio right there is equal to an index of refraction. So when light interacts with a boundary between two different materials, if this is the boundary here, we have one material here, one material there. If we have an incident ray hit that boundary of light, and this is a normal plane, we will have a reflected ray and we will have a refracted ray. Now, and this angle here is the same as the angle here for the reflected ray, and our refracted ray is some arbitrary angle. As this angle increases, our refracted ray, eventually is eliminated at a critical angle, we call it. And this property we call total internal reflection. And this is the property that fiber optics use for light to propagate through the fiber. So if we have a fiber, this is the core here and the cladding around it. And so we have two different materials here. We have a N2 and a N1 for our fiber sizes. So with total internal refraction, you have light propagating through this core here, and it will just bounce back and forth through the core until you reach the end of the fiber. And that's pretty much the basic of how fiber optics work. It is still relatively a new technology, so the costs are relatively high. It started off in the 1970s, I believe, and it started in commercial use in the 1990s. So the costs are still high, but as advances are continually made in the field, the cost will continue to go down. So some advantages of fiber versus copper. Fiber, you can lay a cable down for 2,000 to 3,000 kilometers before you need a repeater station for the signal. Whereas with copper, you need to have copper and microwave systems as well. You can go 50 kilometers before you need a repeater station. And remember, repeater stations cost a lot of money. Next, data rate. I'll start with copper first. Copper, you get about 1 to 4 gigabits per second. That is about the limit of what you're going to get with copper. You're not going to get much better. You try any harder with that, you'll just get noise instead of a signal. Next, we have fiber. Fiber, we're currently at somewhere between 60 gigabits and 100 gigabits per second. Theoretically, we can get up to 2 terabits per second. Now, that is quite the difference, a few orders of magnitude greater. I think I'm kind of running low on time, so I'll just tell you some other advantages real quick here. Fiber is immune to electrical interference. You can string up along a power line without any ill effects or minor ill effects, whereas copper, you have to take those into account. Safety hazards, you don't have electricity running through fiber, so you don't have to deal with electric shocks or sparks, whereas with fiber, you do have to deal with laser emissions, so eye protection would be required. And then increased security, you actually have to break the connection in fiber for you to tap into the signal, whereas with copper, you don't. And I think that's about 5 minutes there. So if there are any other questions for me, I can try to answer them for you. Thank you.
So what is the cladding made of?
They're actually, you can do glass, or glass, plastic, or plastic, plastic. So you have, the cladding's like that, if you kind of think of a 3D. So it's just, it's a very minor difference in the material structure, but it's just enough for it to continue on like that. It kind of depends on what type of system you want. If you want just like a small ranged short system with high losses, you can do plastic. If you want really good data rates, you want to have glass. Yeah.
You said fiber optic technology is expensive. What is the expensive part? I can't imagine a little bit of glass stretched out would be very.
We have to think about all the, well, you have lasers, which are expensive in them, or you can use LEDs now. The glass itself, you have to manufacture the index of refraction. For single index fibers, for single mode fibers, you only have to kind of deal with this kind of step. Whereas if you want a whole bunch of different modes through that fiber, you actually have to have a gradient occur in this cladding, or in the core itself. So different modes will propagate properly, because each wavelength will be affected by your index of refraction in a different way. That answer your question? Okay.
What is the physical maximum? Why are you saying 2 terabytes a second?
Well, my professor told me that was what it was. I believe that just for one single fiber, you can get much more than that if you decide to multiplex them together. I know they've gotten up to 1.1 terabits per second multiplexing them already, but it's also over a short distance, and I think it's like 5 or 10 fibers that they were using at the time. It's pretty much related to the bandwidth, though, that you can travel through that fiber. Any other questions? All right, thank you.